So we're looking today at a question that relates exactly to what we were doing yesterday. So we've learned one inference test so far, which is a one proportion Z interval. And you will learn that name if you don't already have that in your mind. Here are the results that we got from this. So between D and B, those were the two that we were thinking about. Okay, so let's look at this real quick, and we'll figure out why it's one versus the other. I was supposed to close down the poll. I don't think I did. Okay, there it is. So luckily, we don't have to do too much with this. They actually do a lot of the math for us. The one thing we need to know is p hat. We need to know the sample size, and we need to know our critical value, Z star. Luckily, that doesn't change for any of these answers. So 450 out of 1,250 makes a 0.36. P hat in is 1,250. And our Z star is going to be 1.96 because it's a 95% confidence level. We could look that up, but we don't need to because all of them are 1.96. So anyways, it comes down to just the standard error calculation. And we know that the standard error calculation for proportions is going to be square root of p hat times 1 minus p hat divided by n. And so the reason is between B and D, those are the only two that are set up the right way. D is correct. And the reason B is not correct is this 10% thrown out here is part of the prompt. It's part of the question that was asked. And we have to understand that the actual sample proportion that we calculated was 0.36. So we don't want to use the 0.1 right here when we're doing our standard error. All right, so hopefully that makes sense. The 0.36 is the proportion of people who would cut their driving by 10%. And that 10% has nothing to do with the actual proportion. Okay. So let's look at our agenda today. We can see there's a lot of stuff to go over. I don't know that we're going to get through all of it. I can almost guarantee we're not going to get to this practice down here. But we are going to be looking at how to do a confidence interval for means. Yesterday it was all about proportions. Today it's all about means. And we have to introduce some new concepts today, which is why we didn't just throw it all out at the same time. But I wanted to run through this example from yesterday. And this is, we had two examples where we ran through a process. We didn't have time to go through the full thing. So maybe you looked at this, maybe you didn't. I'm going to bet that you didn't look at this, but that's okay, we can now. So remember, this whole idea is we want to have a format, a template, something we can fill out that shows all the important information so that anyone reading your answer will be able to find what they're looking for. And so there's a logical flow to this. We want to just start off by saying, what is it that we're trying to solve, or what is it we're trying to estimate, that is. And in this particular case, there's 415 of 1,423 randomly selected Arizonans recently said that they don't plan to vote in the upcoming election. Construct a 95% confidence interval for the true proportion of Arizonans who won't vote in the election. Okay. So what we're trying to estimate is the true proportion, P. We're using P hat, but we're trying to estimate P. And this is the true proportion of Arizona voters who won't vote. And we could make it even more clear, won't vote in the upcoming election, but we have the idea. Confidence level here, they're asking for a 95% confidence level. Identify the appropriate inference method and check conditions. Name of the procedure here, we only know one. It's the one proportion Z interval. Okay, and we're going to learn why it's called a Z interval today, because we have different types of intervals. And the conditions, we need to make sure that this was a random selection. We need to make sure that it's not more than 10% of the population. And that allows us to simplify our calculations, and we need to make sure that it is normal. Okay. And I know yesterday we just put large counts there, but essentially we're checking normality when we do that. Was it random? Randomly selected, yes. So I'm going to put a check mark. I'll draw an arrow coming up to that so that everyone can see we know it's random. 10%, yes, 1,423 is the sample size, and 1,423 is less than or equal to 10% of population. Is it normal? In this case, does it meet the large counts condition? So now we do n times p, and n times, well, p hat, and n times 1 minus p hat. Now, remember, we're essentially going to get the 415 when we do n times p. So that's 415. And then whatever's left over out of that. Now, you can actually run through and do the calculations. I'm going to skip through this part of it. So, except to get whatever this number is. I don't want to do mental math. There it is. 1008. Both of these are greater than or equal to 10. So we've met that condition. We are good to go on all three conditions. And again, I know I throw this out there and maybe I'm acting like you should already have it memorized. But I mean, we're going to do so many of these, and I know I repeat myself here, but we're going to do so many of these that you will learn all these conditions in just second nature. You'll do them. If the conditions are met, perform these calculations. We want to first of all have a general formula. And this is where this comes straight from the AP formula sheet. So we can say it's the stat plus or minus the critical value times the standard error. Okay. The specific formula. Now, before we do that, let me just say, we're going to use the same general formula when we look at our confidence intervals today for means. That won't change, but the specific formula will. In this case, my statistic is p hat plus or minus a z star for my critical value times the square root of p hat times 1 minus p hat all over n. And now I can actually plug the numbers in, get these values. I didn't ever calculate what p hat is in this case. It is 0.292. So I can write that up here. And we'll call that good enough. So I have 0.292 plus or minus z star for 95% confidence interval. I bet some of you can remember what that number should be. What is our critical value for 95%? 1.96. And I should clarify, that is the critical value for z star at 95% confidence level. All right, p hat is oops, sorry, I was thinking wrong. 0.292. 1 minus that is going to be 0.708 divided by our sample size of 1,423. And now we can just plug that in and get our confidence interval. So we would put this in a different order. So that's 0.269 that I'm seeing. I got 0.268 and 0.316. Obviously, there's no real difference between those numbers. That's based on how I rounded. So my answer isn't better than this, but we would want to put this in order of the smallest to biggest. So we'd want to put our 0.269 and then 0.315. But yes, that is correct. So now we can conclude this and we can write out what a good conclusion would look like. All right, and so hopefully in your head, you're already kind of remembering the way this starts. We are 95% what? We are 95% confident that the interval from 0.269 to 0.315 captures the true proportion of Arizona voters who will not vote in the upcoming election, ... So we could write that. I'm just going to save a few seconds. All right. So there it is. That's the full process. Again, you don't have to follow it to the T. You don't need to follow it exactly at all. You just need to have this information in there somewhere so that there's no doubt about what your thought process was. And there we go. That's all well and good, I hope. I'll leave it here for a few seconds. If you want to take a screenshot of that, if you think that would be helpful to have, it'll be up there for another 5 seconds. And now we're going to move ahead. Now, let me go ahead and say, if this was an FRQ, they probably wouldn't be phrased exactly like this. In fact, they might give you a setup, and then it might give you a question like this. Your friend thinks that this election is historic and that record numbers will come out to vote. He claims that 3/4 of all eligible voters will vote. Is his claim plausible? The way we discuss plausibility in this sense is, of course, if 3/4 of eligible voters are going to vote, then that means he's predicting we're going to get a true proportion of 0.25. This is based on our previous work we did. We were estimating the numbers who won't vote, the proportion that won't vote. So he's saying it's going to be 0.25. Our interval went from 0.269 to 0.31. I just forgot it. 0.319? 316, thank you. There it is. So this is our 95% confidence interval. Is his claim plausible? Right. Why is it not plausible? Yeah, it doesn't fall in our range. So now we can't say that's not true because ours could be one of those intervals that doesn't capture the true proportion. But we can say with 95% confidence, I'm not going to write this all out, but with 95% confidence, we can say that his claim is not plausible according to our data because it falls outside of our confidence interval. We're not saying he's absolutely wrong, but we're saying according to our data, it's not likely. Okay. So, any questions on this before we move forward? All right. And I hope that just going through this a few times, it's already starting to seem like, okay, it's really not that bad of a process. It might seem time consuming and like a laborious thing at first, but hopefully before too long, you're like, oh, it's really not that bad. Okay, so now we're going to do this. This is where we're going to spend the rest of our class time on today. Because I really, really want to know if Nabisco is lying to us, I decided to take the average weight of an Oreo cookie to determine if the average weight was less than advertised. I select a random sample of 30 cookies and found the weight of each cookie in grams, and the mean weight, X bar, was 11.1921 grams with a standard deviation of 0.0817 grams. We're going to make a 95% confidence interval to estimate the true mean weight of Oreos. Okay, what is our point estimate here? No, I was right. 11.1921 is the point estimate. So if we did nothing else with this, our best guess would be 11.1921. But of course, we know this was a sample. Maybe we got some smaller than average or bigger than average, whatever it is, Oreos that haven't had like slightly more cream or whatever the case. So our point estimate is this. And now we want to figure out the following. What is our population going? What is it? Not, anyways, what's the population for this problem? No? All the Oreos. I guess we should say all the Oreos of a specific type. Like if these are basic Oreos or are they double stuffed? But I mean, why would you buy regular Oreos when double stuff is available right next to it? I don't get it. What's wrong with people? Okay. Now, maybe it's worth it right here to talk about, I mean, I keep saying we're doing inference, right? But what does that actually mean? We have a sample of 30 cookies and we're trying to make some kind of, we're just trying to draw some kind of conclusion about all the Oreos that exist based on just 30 of the Oreo cookies. And so that is inference. So we have deductive logic, we have inductive logic. We can either deduce something, we can infer something. And so in this case, we're inferring. We're saying, I have this many cases of something, and I've determined this statistic based on what the small sample. So what can we infer about the entire population? All right, and that's, anyways, so when we talk about inference, it's always drawing conclusions about a population from a sample. What's the parameter of interest here? The true mean weight. Here it is. The sample, what is our sample? That's the 30 cookies that we had. So I'll just put 30 Oreos. You know, this was hypothetical. This is, I pretended like I did this, but I would have. I don't have a scale at home. That's why I didn't do this. Yeah. And what's our statistic? So let me actually write this. The parameter that we're interested in is mu. So what's our statistic? Nope. Do we remember what we call the mean of a sample? No, it's X bar. So our statistic here is X bar. So basically, remember, if it's a sample versus a population, sample would be X bar, population would be mu. Or if it's a parameter, population parameter, yeah, then it's the mu. So the X bar is this, which is the sample mean weight. Okay. So any questions on that? All right. So we still have the same prompt. Now we're going to check our assumptions. We're going to do this one by one. Is it random? Is it? Yes. How do we know it's random? There it is, random sample. All you have to do is look for those words. This is the easiest one to check. Yes, random sample. That means we know it's an unbiased estimator. So that's good to know.
If it didn't, what would you say?
That is a good question, because it is possible to have a problem, even in FRQ. Normally, you can assume that all the conditions are going to be met. But if it's not met for any reason, what you can do is you continue with your analysis, but with a caveat, you say, we didn't meet the 10% condition. So these results might not be accurate. We didn't meet in this random. If it's not random, it can't be fixed really. So you can just say, I don't think you'll ever run across that situation. So if we think through with the conditions again, if it's not random, it's not going to be a fair estimator of the population. And you can't fix that with any kind of mathematical tricks. If it's not 10%, you can make some corrections to your calculations, or you can just say, these might not be accurate, I might be off a bit. If it's not normal, if it doesn't meet the normality condition, then your numbers could be thrown off a bit, depending on how bad it misses normality. So if it's only slightly skewed, then that's not the end of the world. But anyways, the short answer to that is just note that it didn't meet a condition and move forward, and then say at the end, these results might not be accurate. All right, our next condition, 10%. Did we meet the 10% condition? Yep. How do we know? There's a lot of Oreos. I think there's more than 300 Oreos in the world. So yeah, and we would write something to this effect. I'm not actually going to take the time to do it, but yeah, the sample of 30 is less than 10% of the population. And because of this, we can use our simpler calculations. And like I've mentioned in the past, there are, I believe if I'm remembering the name, I think they're called hypergeometric distributions. There are calculations you can use that account for sampling without replacement, but we don't need to worry about that. And the last condition, is this normal? How do we check normality here? Anyone remember?
Something to do with standard deviation.
No? That's a good thought. So Kevin was throwing out the large counts condition. This is where we have to be careful. Large counts only works with proportions. We don't have proportions here, so we don't have a P to use. So this is where we have there are a few options on this, but basically we are using the central limit theorem, which, if you ever write CLT, everyone who's reading your AP test is going to know what CLT is. Central limit theorem that says, as long as you have a sufficiently large sample size, then your sampling distribution will be approximately normal. And the number that we need is that our N has to be greater than or equal to 30. That's our sample. So there we go. So that's why I picked 30 as the sample size. We did meet the central limit theorem. There are other ways around this. And maybe it's worth talking about a little bit. So there are 3 ways that you can meet normality with means. You can meet the central limit theorem if it specifies that the population is approximately normal, then your sampling distribution will be approximately normal. All right, so remember, the central limit theorem says that no matter the population size, your sampling distribution is going to be approximately normal if it's a big enough sample size. But if it tells you at the beginning that your population is already approximately normal, then your sample size doesn't matter. You're going to get an approximately normal sampling distribution. And we'll definitely reinforce these ideas. You don't have to have this memorized today. So either the central limit theorem is met, the population is approximately normal. So I'll say we met this one right here. We're good to go. We didn't actually meet this. We can assume that the population is approximately normal of Oreo cookies, but oops, didn't mean to do that. But we don't know for sure. And then the other one, let's just say this third one never happens. But the third possibility is that if you look at the distribution of your sample And if the distribution of the sample is approximately normal, then you can move forward and assume that it's normal. But that requires taking your sample, plotting it in a histogram, deciding that it's approximately normal, and then moving forward. So it's worth talking about right here, but we never use this one in practice. So I'll just say, right here, never used in this class. Okay, and I just covered that up. But if it's normal, we can use our normal CDF calculations, which makes our life a little better. Okay. Got a little bit in the weeds on that, but it's some important content we need to cover, and I will definitely bring that up again, okay? Oh. There, I didn't realize I had a slide on this. There we go. So there it is. That is in the presentation. If you want to refer to this later, you can find this under today's presentation. So that's what I was just talking about. All right, now we already decided that it was approximately normal based on the central limit theorem. So now we can move forward. Now we want to start thinking about our calculations. We need to know it's the same thing as before. We have a confidence interval that has statistic, critical value, and standard error. So nothing has changed. The statistic is already known. That's our sample mean, that 11.1921. So let's talk about the other part. This is a little bit of review. When you have a sampling distribution of means, you have a standard deviation, which is the population standard deviation divided by the square root of n. And the problem, of course, is we don't know the population mean, or we don't know the population standard deviation. We're going to have to use X bar. Oh, so let's talk about this now. Sorry, that was talking about the means, but we're good with that. We don't know the population standard deviation, which means we're going to have to use the sample standard deviation as our estimate. So there's no real difference between our standard deviation for a sampling distribution on the left and our standard error for a sampling distribution of sample means on the right. But we do call this one the standard error. So just keep that terminology in mind and we're good to go. And they will always give you the standard deviation, or sorry, the sample standard deviation. That will always be known for you. So that's not going to be something you have to calculate. So here's what we've got. If we plug in these values, our statistic is going to be X bar. The standard error is going to be this right here. So I'll pause right there to make sure there's no questions on that. Do you guys, is anyone confused about how we got this right here? Okay. Just want to make sure I'm not going too fast. So now it's the standard error. But now we need to know the critical value. And this is not a Z star. This is where we have to introduce the new concept. This is mostly kind of everything falls into line so far, but this t distribution is going to be new. When we were working with proportions, the only parameter being estimated was the population proportion. Keep in mind, the only statistic we used was p hat. And the standard error for the sampling distribution of sample proportions is calculated this way. Now this is pretty straightforward because we only needed to know one statistic. The n is not a statistic, it's just the sample size. So p hat was our statistic. We can use it, plug it in, and we get our standard error. When we're dealing with means, we don't just have one parameter estimated, we have two. The population mean is being estimated by the sample mean, and the standard deviation, the population standard deviation, is being estimated by the sample standard deviation. So there are two unknowns, and that increases the uncertainty in the confidence interval. Okay, so it's one thing to say, well, we don't know the true population proportion, so we'll just guess that it's the same as the sample proportion. But it's another thing to say we don't know anything, and now we're going to use 2 guesses to estimate the true population. So here we go. Let's look at the t distribution. Okay. And the t distribution will maybe at first look like it doesn't even make that big of a difference. So the t distribution in this is this kind of a tan, whatever color that is. And the blue line represents a normal distribution. So visually, I couldn't look at a curve and decide that it was a normal or a t distribution. They don't look much different, especially notice what happens when we go from a degree of, and we're going to talk about degrees of freedom next. When I go from degrees of freedom 1, that's a pretty big difference. But when I get up to even here, like degree of freedom 7, there's not much difference. And as I go up, it doesn't change very much. When I get up to 30 degrees of freedom, it's practically the same thing. But here's the key difference. Notice for all of these, the tails are fatter. All right. And what this means is that if I am right here, in order to capture 95% of the data, I actually have to make my critical value bigger than I would for a normal distribution. So, and that might not make sense the way I just said it, but let's look at this. You can see that the data in the normal distribution is more centrally located than it is in the t distribution. There's more data out on the extremes for the t. Let me go to the extreme example. I'll just go with that one. So for the same area, if I go to 1 standard deviation away, look at this. In a normal distribution, 68.3% of the data is found 1 standard deviation away. But in this t distribution, only 57.7% of the data is found 2 standard deviations away. When I move out to 2, it's 95% of the data for the normal. It's 82% of the data for the t distribution. So if I want to capture 95% of the data, I've already got it here with the normal, but I have to have a bigger t critical value. In fact, I have to go all the way out to, wow, 95, right there. Notice right here, this number. I had to go all the way out to this negative 4.3, basically, a critical value. So whereas with the normal distribution, I only needed a z star critical value of 2. With this, I have to go all the way out to 4.3. So the important thing is that we're casting a wider net with means because we're using a t distribution. Is this making sense?
Yeah, what is it?
The t distribution is basically, just in essence, it is a, and we're not even going to get into the mathematics behind the curve. But essentially it is a curve that's accounting for degrees of freedom and more uncertainty with having multiple unknowns. So it's essentially just fattening the tails.
So it's just a mean thing. It's just like,
Yes, only for means.
scenario we use it in.
You only ever use t distributions for means. Yeah, and actually that's good to point out now. That's something that will make very, very obvious, but we can make it obvious from the beginning. If you're dealing with proportions, you're using the z, which is your normal distribution. If you're working with means, you're going to use your t distribution. Now, we can't just jump right in and use it because we need to understand what degrees of freedom are all about. So if we want to get more information on the t distributions, just to make more sense of that, we can come back to that later. But understanding that a t distribution basically just has fatter tails and we need bigger critical values, then that is a good starting point. Okay, so we're going to talk about degrees of freedom. We're going to do 2 examples. So imagine you have a collection of 7 hats, and for the next 7 days, you want to wear a different hat. On day 1, how many options do you have? 7. You can pick any one of those 7. So this is going to get redundant. Day 2, you've already worn one of the hats, so now you can only pick from 6. then, all right, then 4, then, all right. On the second to last day, you got to 2. Now, on the last day, how many choices do you have? 1. Do you really have a choice at that point? No. I mean, if you're sticking to this idea of wearing different hats every day, then you're down to the last one. You have to wear that last hat. So you had the freedom to pick what you wanted to wear every single day except for that last day, meaning your degrees of freedom in this case was 7 minus 1, 6. You had 6 days of options, 1 day where it was forced for you. Okay. So if we tie this back into numbers, because that is an abstract example, but easy to follow, this will also be pretty easy to follow. Imagine I tell you from the beginning that you have a sample mean of 10 and a sample size of 4. We want to go with simple numbers here. So just imagine this is true. Just give me a random value. Keep it whole numbers to make the math easier. But what is a possible value for the first individual in our sample? 10. Maybe the second one has a value of what? 9. And the third one has a value of what? 11. So at this point, we now get to our fourth individual. What does his value have to be? His or her value. I already told you what the sample mean is. And we randomly picked, it has to be 10. So in this case, the first 3 we could randomly decide, and if we wanted to make this 14 instead, just to make it, spice it up a bit, right? So I add this up, so that's 19 plus 14 is 33. So there we go. Now we have 33, but we know for a sample mean of 10, we have to have a total of 40, which means the last guy has to be 7. We didn't have a choice for what the last number was if we're targeting a specific sample mean, but we did have a choice for the first 3. All right, so in this case, we had freedom to decide the first 3 values, but the last one was forced to be a specific value to make the sample mean calculate correctly. Therefore, our degrees of freedom is 4 minus 1, so 3 degrees of freedom. And this is the main takeaway. Degrees of freedom, conceptually, maybe it's a little bit weird to think about, but straightforward as far as a calculation. The degree of freedom is always going to be 1 less than the sample size. This gets a little bit trickier when we're talking about 2 means and when we get into our chi-square calculations, but they never get too bad. Let's just say that. So the degrees of freedom is going to be sample size minus 1. Okay, and so what does that mean? All right. We can now use the table B in the AP formula sheet to find our critical value for any problem. And we're going to call this T star since it's a T distribution. So now whenever we're talking about a critical value, if it's proportions, we're using Z star. If it's means, we're using T star. So there it is. And this is what you were asking about a minute ago, Leo, and now we're making it clear. If it's means, you're using T star, proportion Z star, and there we go. I don't need to keep saying it. So now we've got a critical value, and this is going to be a little bit hard to read, but hopefully clear enough to read it. And I want to point out, first of all, that as you move right to left, your critical values get bigger and bigger. And we already talked about this because this is the same as your confidence level down here. As your confidence level gets bigger, then you're casting a wider net because you want to make sure you capture, in this case, 99.9% of all confidence intervals should capture the true mean. So you want to have a really wide confidence interval. Now, you'll also notice as you go from top to bottom, the values get lower. The only row that we used yesterday was this infinity. And this represents, for proportions, it's an infinite amount of degrees of freedom. But when you're all the way up here and you only have 1 degree of freedom, if you remember imagine this is a normal distribution. That diagram I showed you a minute ago had a t distribution that looked like this. I didn't draw it very well, but good enough for our purposes. So if we want to capture 95% of the data, rather than just going to 2 standard deviations away, we need to go really far out. We might need to go that far out to get 95% of the data. So as your degrees of freedom get smaller and smaller, we have to go further out to capture 95 or 90%, whatever confidence level we're talking about. And I'm going to pause right there and make sure everyone's good with that concept. Are there any questions? Okay. So as long as we understand basic idea, the more degrees of freedom you have, the smaller your critical value is going to be. And maybe that's just the main takeaway. That's all we really have to think about. So in our case, we had 30 in our sample size, 30 cookies. So what's our degrees of freedom? (29) Degrees of freedom, remember, it's just your sample size minus 1. So that's going to be 29. So here's what I want to do. I want to focus on this row. I'm not quite pointing to it, but 29 right here. And I've forgotten my example. Did I say, was it 95% confidence? Okay, 95%. So now, luckily, we just need to find where the 95% confidence level is. And we're still looking at this bottom right here. So we can just go up. So it's 2.045. Okay, so easy enough to read that chart. Find your degrees of freedom, find your confidence level, and you're good to go. So 2.045, and we can compare that to the Z critical value for 95% is 1.96. So we're going 1/10 of a, or sorry, 1/100, no 1/10, that was right. 1/10 of a Z score further out to capture 95% of the data. All right, that's probably good to go. 2.045, we'll remember that number. And this is what we call a one sample t interval for mu. We also call it, just a second. We can also call that just a one sample t interval. The for mu is not necessary to say, but one sample t interval. We had the one sample or one proportion z interval yesterday. This is a one mean t interval. As long as you get the point across. Okay, I don't want to dwell on that. So now we've got this all worked out. We can see from the table that our 2.045, we found that. And here's the calculation we have to do. And there you go. I went ahead and did the calculations on this one. And there it is. So the confidence interval is going to go from 11.1616 grams to 11.2226 grams. All right. And moving forward with this. If Nabisco claimed that the mean weight of a cookie is 11.3 grams, would you find this claim to be likely? No way. Those liars. Corporations. What are you going to do about them? All right. So it falls outside of our confidence interval. So we could respond with 95% confidence. We can say that this is unlikely to be true because it falls outside of our confidence interval. And you wouldn't just say it, you would say because the mean weight from our the claimed mean weight falls outside of our confidence interval. Okay. Maybe I'm being a little lazy by not writing it down, but if in your head you can come up with a way of saying that conclusion, then you can just copy it down onto the page. So now the question is, do we have enough time to do that? And you know what? We're going to pick up tomorrow and do these examples. So we just are going through the conceptual stuff today. You can go ahead. I'm going to skip past this. We're going to go through these examples tomorrow. Wow, I have 2 examples, but we're only going to do one of them. No, we might do both. But whatever the case, here's your homework for tonight. I encourage you to go through and look through it. And yeah, come back tomorrow for more fun. All right, have a good night. If you have any questions, stick around.